This is section R.7, radical notation and rational exponents. Again, remember the word rational means fractions. We're looking at fractional exponents in this section. Some definitions. Square roots. Definition. Let a be a non-negative real number. So that means a is greater than or equal to 0. A square root of a is a real number b that satisfies b squared equals a. Some notes about this. Number 1 says a is not allowed to be negative. We don't take square roots of negative numbers. Number 2, b is called a square root, not the square root. There is a difference. Number 3, there is no notation for a square root. In spite of what you're thinking, there is no notation for a square root. You just have to actually write the words, find a square root of whatever. Some examples. Okay, these examples are really just illustrations. Number 1, 7 is the square root of 49, since 7 squared is equal to 49. Number 2, negative 7 is also square root of 49, since if you square negative 7, you also get 49. Number 3, 11 is the square root of 121, since 11 squared is equal to 121. And the same thing will happen with negative 11. It's also square root of 21, because if you square negative 11, you get 121. Notice this will always happen, that you'll have a positive 1 and a negative 1, except for one case, and that's 0. 0 squared is 0, and minus 0, there's really no such thing. 0 is neither positive nor negative. Okay. Note, b and negative b are both square roots of the same number, since b squared and negative b squared both become square root of b squared. We want to get rid of this problem. Okay, on mathematics, if we have a problem that we want to get rid of it, we do it with a definition. So, principal square roots. Definition. Let a be a non-negative real number. The principal square root of a, and it's noted like this, probably what you were thinking of when we said a square root of a, and it's read the square root of a, is the unique non-negative real number b that satisfies b squared equals a. Notice we've inserted this word non-negative for b as well, so b is not allowed to be negative. So some notes on this. The square root of a is greater than or equal to 0 for any real number a. If you recall, we had something like that earlier, that it was never negative as well, and that was the absolute value. So there must be some sort of connection between absolute value and principal square roots. Some examples. The square root of 64 is equal to 8, since 8 is not negative and 8 squared is 64. We don't get negative 8 out of this. The square root of 100 is equal to 10, since 10 is not negative, and 10 squared equals 100. You don't get negative 10 out of that. But what if you did want the negatives? The negative square root of 81 is negative 9. Okay, so the minus sign that's in front of the square root, this minus sign, is the same as this minus sign that's in front of the 9. So if you want the negative square root, you actually have to put a minus sign in front of the square root symbol. The negative square root of 25 is negative 5. Okay, again, this minus sign is this minus sign. So if you want the negative number to come out from this principal square root, you actually have to put the minus sign. In most situations, we must use a calculator to approximate a square root. So let's try some examples. Let's approximate each of the following to the nearest 10 thousandths. Now remember, 10 thousandths is going to be 4 decimal places. Okay, so remember it goes tenths, hundredths, thousandths, 10 thousandths. So the square root of 23. Okay, if we were to do this on our calculator, so I've got my calculator out. Okay, the square root is the thing in orange. Okay, I'm using another TI-83 calculator instead of the one I used earlier in some of the other slides, or actually some of the other videos. So second, oops, it went off, didn't it? Turn it back on. So second square root. Now notice I did open a parenthesis when we got the square root key. We have to remember to close it. 23, close. Can we get this block? Okay, if I want to go to the nearest thousandths, remember 10 thousandths is 4 decimal places. I can actually do that with the mode. So do mode, scroll down to float, go over to 4, because remember it's going to be tenths, hundredths, thousandths, 10 thousandths, and press enter. Okay, to get out of this menu, just do second quit. So quit. And if you press enter again, it's now to 4 decimal places, 4.7958. Now, until you change the mode, it'll round everything to 4 decimal places. Even if you just key in 0, it's going to do it out to 4 decimal places. But anyway, for the first one, I get 4.7958. Okay, so 10 thousandths again. This is our setting on the calculator. It's 4 places right at the decimal point. In our mode setting on the calculator, we can set the float to 4. That way the calculator will do all the rounding. Now again, remember, the calculator will keep rounding to 4 places until you move the float back to float. So I get 4.7958. Okay, if I do number 2, again, if I take out the calculator, okay, the negative sign. Okay, it's this sign for the negative a number, not this one. That's the operation of subtraction. Second, square root 105, close the parenthesis, the calculator open, and we get negative 10.2470. And you do need the 0, otherwise you don't have 10 thousandths. And for number 3, we do the same thing. We get negative 9.3808. And for number 4, we actually have an operation. So if I do it exactly like it looks, let me clear this out. Let me move my calculator over. 5 minus 4, second square root, 23, close parenthesis. We get negative 14.1833. Okay, now you need to be sure you can get these on your own with your own calculator. Please don't switch calculators when you go to a test. Use a calculator that you're familiar with. Okay? So if you can't get these answers, you might want to find out what's going wrong. Higher roots. Higher meaning higher than a square root. So definition, let n be a natural number greater than 2. So it'd be like 3, 4, 5, and so on. Then, number 1, if n is even and a is a non-negative real number, then the principal nth root of a, and it's noted like this, we put a little n there in the valley that was in the radical symbol, is unique non-negative real number b that satisfies b to the n equals a. Number 2, if n is odd and a is any real number, then the nth root of a, denoted by the exact same thing, is unique real number b that satisfies b to the n equals a. Okay, when you look at n, you'll know whether or not it's even or odd. Okay? Notice if it's even, everything is not negative. If it's odd, there are no restrictions. Some terminology and notes that goes with this definition. The nth root of a is called a radical expression or simply a radical. Number 2, n is called the index of the radical. If the index is 2, then it is not written. Thus, the second root is really the principal square root. Okay, so we've actually seen a special case of this. So we don't write an index of 2. It's kind of like we don't write denominators of 1, we don't write coefficients of 1, and we don't write exponents of 1. We don't write an index of 2. That thing is called the radical sign or radical symbol. Notice it doesn't include the index with it. So again, it's kind of like the square root is the smallest root we take. Number 4, a is called the radicand or expression under the radical. Number 5, evaluating a radical expression is called extracting a root. So in addition to what you call evaluate, that's the technical name, extract a root. Number 6, it is not possible to evaluate an even root of a negative number. Again, we do not work with imaginary numbers. You take any number and square it, take any number to the 4th power, take any number to an even power, and it won't be negative. So no even roots of negative numbers. That problem will come back to haunt us in another section. Number 7, it is possible to take an odd root of a negative number. The result will be negative. So an odd root of a negative number is negative. The odd root of an even number, the odd root of a positive number is positive. Remember, no even roots of negatives. Number 8, if n is even, then the nth root of a is greater than or equal to 0 for all real numbers a. Remember, the principal square root was a special case of this. In number 9, if n is odd, then the nth root of a has the same sign as a. Again, when you look at the problem, you will know whether or not the index is even or odd. It's not something you have to worry about. You'll actually be able to see it. Okay, so some illustrations of this. The cube root of negative 27. Okay, it's negative 3, since negative 3 cubed is negative 27. All right, negative 3 times negative 3 times negative 3. Number 2, the 4th root of 625. It's equal to 5 because 5 to the 4th power, right, the index matches the exponent there, is 625. As another illustration, the 5th root of 32, it's 2, since 2 to the 5th is equal to 32. Notice I had to pick some special numbers in order to let me do it. In general, we need a calculator. For the TI-83-84 family of calculators, the nth root key is found by pressing the math key. So again, however, before pressing the math key, you must first enter the index of the radical. Okay, that's kind of disadvantage, like, oh, I forgot to put my index in. The result of pressing the math key gives the following menu. Okay, you're going to have this. When you press math, you got this. Okay, the first one is how you make the last calculation go to a fraction. This is making the fraction go to a decimal. This is actually taking it to the third power. So that's the cubed. This is the cube root. And notice it opens a parenthesis. This is the nth root. The TI-8384 calls it the xth root. Okay, and notice it doesn't open a parenthesis. I believe it's the only function on the calculator that doesn't open a parenthesis. You can open one if you want, but you'll have to remember to close it though when you're done. So notice that choice 4 is the cube root and choice 5 is the xth root. So we'll use choice 5 for approximating nth roots. So for example, to calculate the 7th root of 1,874, we have the following keystrokes. Okay, first do the index, 7. Then press math. Then choice 5, the xth root. You can actually just press 5. And then press your 1,874 key, then press enter. Your screen should look something like this. So this is the 7th root. Now notice it looks like 7 times the square root of 1874, but it isn't. If I were to do this on the calculator that we have here, okay, turn it back on. Okay, now remember, we had set our float to 4. So if I do mode, let me put my float back to float, then quit this. So I do 7, math, choice 5, 1, 8, 7, 4, enter. And I get the same thing that is on our screen there. So the 7th root of 1,874 is about 2.934529721. So later on we'll see other ways to calculate roots on the calculator. Okay, now when you're going to approximate the roots on the calculator, pick a method you like and stick with it. You don't need to learn 100 different ways to do one thing. So some examples. Approximate the following. Round your answer to the nearest 100 thousandths. So now remember, 100 thousandths is going to be 5 places right at some point. So we'll set our mode float to 5. So that way the calculator does all the work. So let me turn this back on. Clear that out. Mode. Scroll down to float. Scroll over to 5. Press enter. And now all my calculations will be done to 5 places. So our first one, the 7th root of negative 4872. So our keystrokes are going to be 7. First the index, then math, choice number 5, negative 4872, press enter. You get something that looks like this on your screen. So to 5 places, it's negative 3.36369. So again, if I take out our calculator, 7, math, choice 5, negative 4872, enter, and again I get the same thing. Okay, so there's our calculator. So warning, do not confuse the number in front of the xth root with a coefficient in front of a radical expression. The number in front of the xth root is the index of the radical. It is being plugged into x in the calculator. If you actually want something times an xth root, you have to enclose the xth root along with its index inside parentheses. So the 6th root of 5007. So again, if I take out our calculator, 6 for the index, math, choice 5, 5, 0, 0, 7, enter. I get 4.13615. Okay, now again, be sure you can get these results on your calculator. It's a shame to find out on homework or test by getting it wrong that you can't do it. Okay, let's look at simplifying radical expressions. Okay. This is going to have to be done when you start having to use the square root principle in order to solve your x squared equations. So we've got to learn how to simplify radical expressions. So some note, you will need the document titled A Brief Table of Powers in order to simplify radical expressions. It is supposed to make the work easier. Okay, you don't actually need it, but it is, again, supposed to make the work easier. There are other ways around it. The document can be downloaded from the content browser area of our D2L homepage. It's also in our My Math Lab course as well. It's in the course documents area. Properties of radicals. Now, some of these properties, you would do them even if you were told you can't. So the following properties are valid provided the radicals exist as real numbers and a and b are real numbers. Number 1, if n is even, then the nth root of a to the n is equal to the absolute value of a. There is the connection between principal roots and the absolute value. Notice the index of the radical matches the exponent. Number 2, if n is odd, then the nth root of a to the n is just a. No absolute values. It would be wrong to put them. Now, when you do simplify the absolute value of a, like if you get the absolute value of 7, write 7. Don't leave the absolute value of 7. Now, if you have variables, you're stuck leaving the variables. Number 3, the nth root of a times the nth root of b is equal to the nth root of ab. So, the radical of the product is the product of the radicals. We usually use this property in going from right to left. We want to take one radical and break it apart. The same thing applies to quotients. So the product of the radicals is the radical of the product. Number 4, the nth root of a or the nth root of b is the nth root of a over b provided b is not 0. Again, we usually use it from going to right to left. So the radical of the quotient is the quotient of the radicals. So we'll be using 3 and 4 quite extensively in order to simplify our radicals. Number 5, the nth root of a to the m is the nth root of a to the m power. It's kind of like the exponent that's under the radical can come outside. Usually this is a smaller number to calculate. Like if you take a to the m power, that could be huge. We'll actually be using this to help us a little bit later on. It's 3 and 4 that we use quite extensively to simplify our radicals. Okay, some notes on these properties. In properties 1 and 2, the exponent of the expression of the radical is the same as the index of the radical. If you go back and look, the exponent matches index, exponent matches index. Property 1 is saying that when you simplify even roots, you must put absolute values around variables that come out from under the radical. Okay, with numbers, you can take the absolute value of a number, so don't leave a number inside of absolute values. The variables, you might have to do that. This is because the even root of an expression is never negative. Remember, even roots, it's principal roots. An illustration of this. The square root of negative 2 squared. If I square negative 2, I get 4. And the square root of 4 is 2, which is the absolute value of negative 2. Because remember, that's what I started with. I started with negative 2. Property 2 is saying do not put absolute values around variables that come out from under the radical for odd roots. In fact, if you put absolute values when simplifying an odd root, it's wrong. Remember, with odd roots, the sign of the answer matches the sign of the problem. The only way to avoid the issue of absolute values is if the directions say that you may assume that all variables represent positive real numbers. Okay, that is the simplest way to put it, that all variables represent positive real numbers. The textbook uses these really weird directions that you may assume that no value is the result of taking a negative number to an even power. He's really trying to tell you that everything is positive. Now, because of the confusion between odd versus even index, you do have to have at least a few where you're told not to assume everything is positive to see if you know you're supposed to put absolute values with evens and no absolute value with odd index. So the only way to avoid the issue is to assume everything is positive. Now, if the directions do not say that all variables represent positive real numbers, then you must use absolute values in simplifying even roots. Okay? So again, you hope and pray that it says everything is positive. Simplifying radicals. To simplify a radical means, number 1, have as small a number as possible under the radical. Be aware that the smallest number of the radical can be large. Ideally, you would like the radical to go away. Number 2, all variables under the radical have exponents that are smaller than the index of the radical. Again, we're assuming that you're using all positive exponents. So notice number 2 is kind of easy to make sure that it happens. Just look at the exponents and look at the index. So notice with a square root, the index is 2. That means the variables can only have exponents of 1. With a few exceptions, like if you have bunches of plus and minus signs under there, then there's no telling what could happen to you. So note, in general, simplifying a radical expression is not the same thing as evaluating it. If the radical completely disappears when you simplify the radical, then you've also evaluated it. For instance, the square root of 4 equals 2. You've simplified it and you've also evaluated it. But the square root of 5, it is simplified, even though you have not got an approximation for it. Now be warned, do not approximate unless the directions specifically say to approximate, Because if you're wondering how many places should I carry in my decimal, if the directions don't say, you're not supposed to be going to a decimal. Some examples. Simplify the following. Do not assume that all variables represent positive real numbers. So our first one, I have the square root of 24. Okay, here's the idea. In our brief table of hours, we look to see if 24 is in the n squared column. We look to see if it's a perfect square. It isn't. So we look for the largest number in the n squared column that will divide evenly into 24. So we want a perfect square that's a factor of 24. Turns out it's 4. So we can write 24 as 4 times 6. Now don't use 8 times 3 because neither 8 nor 3 is a perfect square. We're picking 4 times 6 because 4 is a perfect square. So the square root of 24, I'm writing it as square root of 4 times 6. I now use one of my properties of radicals. I can write this as the square root of 4 times the square root of 6. And the square root of 4 is 2. So I have 2 square root of 6. That's your final answer. That's the simplified form. Number 2, the cube root of 24. Okay, this time we would look down the n cubed column. We want to find the largest perfect cube that goes evenly to 24. Okay, this time it's not 4, it is 8, because 8 is a perfect cube. It's 2 times 2 times 2. So this time I'm going to write 24 as 8 times 3. Now please, don't lose the index when you write your work down and you write your final answer. If you lose the index, I'm going to believe that you thought it actually disappeared. So the cube root of 24 is the cube root of 8 times 3. I break this apart as cube root of 8 times cube root of 3, and the cube root of 8 is 2. So I have 2 cube root of 8. Now, this cannot be 2 cubed as your final answer because, after all, if it really were 2 cubed, you would have written 8. So it's 2 cube root of 3. Number 3, the fourth root of 2500. So you would look down into the fourth column to see if 2500 is there, and of course it isn't. So again, you look for the largest perfect fourth root that's a factor of 2500. So again, you go down into the fourth column and look for a number that would divide evenly into 2500. It turns out it's 625. So I'm going to write 2500 is 625 times 4. I break this apart, and the fourth root of 625 is 5. So I have 5 onto the fourth root of 4. Now I have to admit, with numbers it can be kind of difficult. With variables it's a little bit easier. I've got the square root of x to the fourth times y to the seventh. Remember, the index you don't see is 2. And because of the square root, I will need absolute values. So the index of the radical is 2 since we do not see it. The idea is still the same as it was with numbers. Factor the radicand so that one factor is a perfect square and the other is not. For variables, a perfect nth power has an exponent that is a multiple of n. So remember, our n is 2. So looking at just x, we want the largest multiple of 2 that is less than or equal to 14. Okay, 14 is a multiple of 2. So far, this is our perfect square root. Okay, now looking at the y. The largest multiple of 2 that is less than or equal to 7, it's 6. So I'm going to have an x to the 6th join the x to the 14th, but I'm still going to need one y over here. Notice this exponent is 7 minus 6. Okay, now to take the square root, remember, just divide the exponents by 2. So the expression with parentheses on the right side is a perfect square. This expression right here, the x to the 14th, y to the 6th, that's our perfect square. So with variables, to take square roots, divide the exponents on the variables by 2. So don't forget the absolute values. So I have the absolute value of x to the 7th, y cubed, times the square root of y. Okay, now even though it's possible to simplify the absolute value, we're not going to worry about that. Our goal is really to simplify the radical. If you leave off the absolute values, it's wrong. Let's do the same thing with the cube root. The cube root of x to the 14th, y to the 7th. So since we have an odd root, no absolute values will be needed. In fact, if you put them, it's wrong. So since the index is 3, we want exponents that are multiples of 3. Okay, for x, the largest multiple of 3 that is less than or equal to 14. Turns out it's 12. So I'm going to write x to the 14th as x 12th times x squared. This is the perfect cube. So there's my perfect cube. Here's the rest of the x that's not a perfect cube. And notice the exponent is smaller than the index. Now do the y. Okay, for y, the largest multiple of 3 that is less than or equal to 7. It's 6. Remember, the multiples of 3 go 3, 6, 9, 12, 15, and so on. So I'm going to write y to the 7th as y to the 6th times y. So the y to the 6th joins the x to the 12th as the perfect cube, and there sits y with the x squared. Its exponent is 1, which is less than my index. So that's where we left off. Okay, I've broken it apart into two radicals, the perfect cube part, the non-perfect cube part. Okay, this part is already simplified. The exponents are smaller than the index. Okay, to take a cube root, divide the exponents by 3. And remember, no absolute values. So I'll have x to the 4th y squared times the cube root of x squared y. Number 6. The 4th root of 32, x cubed, y to the 7th, z to the 18. Okay, I will need absolute values because I have an even root. Okay, since it is an even root, absolute values. Okay, let's take care of the 32. I want the largest number in the end of the 4th column that will divide evenly into 32. Turns out it's 16. So I'm going to write 32 as 16 times 2. There's my perfect 4th power. Here's what's left over. Now let's start taking the variables. Okay, for x, look for the largest multiple of 4 that is less than or equal to 3. Okay, technically it's 0. So no x's will join the 16. And notice with x to the 3rd, the exponent is already smaller than the index. So x is not coming out from under the radical. Let's go to y. Largest multiple of 4 that is less than or equal to 7. It's 4, right? Because multiples of 4 go 0, 4, 8, and 8 has already passed 7. So I'm going to write y to the 7th as y to the 4th times y cubed. So the y to the 4th will join the 16. The y cubed will stay with the 2x cubed y. So this is where we left off. So I've got 2x cubed y cubed. I'm now going to take care of the z part. For z, largest multiple of 4 that is less than or equal to 18. It's 16. Remember, they go 4, 8, 12, 16, then 20. So I'm going to write z to the 18th as z to the 16th times z squared. The z to the 16th will join the 16y to the 4th. The z squared will join the 2x cubed y cubed. Okay, so that was where we had before, and now we're down to here. Okay, now when you do the 4th root of 16, it's 2. Don't put the 2 in absolute values. You know the absolute value of 2. It's 2. Now for the variables, divide the exponents by 4. I'll have y z to the 4th, and those will need the absolute values. So take 4th roots, divide exponents by 4. And don't forget absolute values. So 2 times absolute value is y z to the 4th times the 4th root of 2x cubed y cubed z squared. Okay, now if you want to, z to the 4th is never negative. You could drag it out from under the absolute values as well. It's only the y that truly needs to be there. Number 7. I have the 5th root of 21, x to the 7th, y to the 18, z to the 20. Okay, since it's an odd root, we don't need absolute values. Again, it'll be wrong to put them. Okay, you're working with the number. Okay, look for the largest number in the 5th column that divides evenly to 21. Okay, it's 1. Okay, 21 is just 3 times 7. There's nothing we can do with it. Okay, let's go to the x. So for x, largest multiple of 5 that is less than or equal to 7. It's 5. So I'm going to write x to the 7th as x to the 5th times x squared. So here's my perfect 5th power, and I'm up to here in what's staying under the radical. Now go to the y. For y, the largest multiple of 5 that is less than or equal to 18. Okay, it's 15. So I'm going to write y to the 18th as y to the 15th times y to the 3rd. The y to the 15th will join x to the 5th. The y to the 3rd will now join 21x squared. Okay, I'm now getting ready to take care of z. So for z, I'm going to find the largest multiple of 5 that is less than or equal to 20. It is 20. So I'll leave z to the 20th as z to the 20th, and it is a perfect 5th root. So I now have the 5th root of x to the 5th, y to the 5th is z to the 20, times 21x squared y cubed. This will stay under the radical, and in order to do the 5th root, divide those exponents by 5. So I'm going to have x y cubed z to the 4th times the 5th root of 21 x squared y cubed. No absolute values. It was an odd index, right? odd index. Number 8. The square root of x squared plus 4x plus 4. Okay, there was nothing in our properties that said we could separate sums or differences under radicals. So what we want to do is we want to somehow factor this. So the square root of x squared plus 4x plus 4 is the square root of x plus 2 squared. This index is a 2. That exponent is a 2. The x plus 2 is playing the role of a in our property. So I'm going to have the absolute value of x plus 2. Okay, you cannot separate a sum or a difference in absolute values either. Just like you can't do it with radicals, you can't do it with absolute values. This is as far as it will go. You cannot take the 2 out from the absolute values. So if you got pluses and minuses, you got to see about factoring. If it didn't factor as something squared, there's nothing we could do. Like if this were x squared plus 4x plus 1, it's already simplified. Arithmetic with radicals. Okay, this is an add, subtract, multiply, divide. So for the trick, we mean add, subtract, multiply, and divide. This is going to be like combining similar terms. So we're not approximating the radicals. So again, resist the temptation to approximate. If you don't see the word approximate in the directions or something about the number of decimal places to carry in your answer, you're not supposed to be approximating. You're supposed to be doing something else. So with respect to radicals, we usually assume that all variables represent positive real numbers. It's just to make our life a little bit easier. Adding, subtracting radicals. Adding, subtracting radicals is really just another form of combining similar terms. So instead of saying like x terms, I'd say something like square root of 2 terms. So however, sometimes we have to simplify the radicals before we can add or subtract them. That's kind of the little trick that you might have to worry about. Let's take a look at some examples. Perform the indicated operation simplify, do not approximate. You may assume that all variables represent positive real numbers, so you won't need absolute values. In fact, it would be wrong to put this. Here's our first one. The 4 times the square root of 5 plus 7 times the square root of 5. It's kind of like you had 4x plus 7x. Okay, it's supposed to make you think 4x plus 7x. So you just add the coefficients. So I'd have 11 square root of 5. And that's your final answer. Number 2. 3 square root of x minus 7 times the square root of 11 minus 7 times the square root of x plus 12 times the square root of 11. So you've got square root of 6 terms and cube root of 11 terms. So I want to combine the square root of 6 terms, I want to combine the cube root of 11 terms. So combine what's in blue, combine what's in green. So I have what? Minus 4 square root of x plus 5 cube root of 11. It doesn't matter in what order you write these. Just be sure you get the signs correct and the coefficients correct. Number 3, okay, a 5 square root of 2 plus 4 square root of 50 minus 7 square root of 72. Hey, the square root of 2 can't be simplified any further, but the square root of 50 and the square root of 72, maybe they can be. See, what would happen if I divided by 2? 50 divided by 2 is 25. Perfect square. 72 divided by 2 is 36. Perfect square. But suppose you didn't notice. So we just went to simplify our radicals. So for the second radical, the largest number in the n squared column that would have yielded 50 is 25. So again, I write 50 as 25 times 2. There's my perfect square. So far I have 5 square root of 2 plus 4 times square root of 25 plus times 2, and now let's work on the 72. So for the third radical, find the largest number in the n squared column that would divide evenly into 72. Okay, it's 36. And 36 times 2 is what I'm going to replace the 72 with. So I now have a perfect square, a perfect square. So now we're going to simplify the second and third radicals. So this is where we left off. Okay, the square root of 25 is 5, that's where that came from. The square root of 36 is 6, and that's where that came from. Okay. I now got to do 4 times 5 and 7 times 6. So I have 5 square root of 2 plus 20 square root of 2 minus 42 square root of 2. I now have nothing but square root of 2 terms, so I can simplify that. Just do 5 plus 20 minus 42. I get negative 17 square root of 2. Square root of 2. Number 4, the square root of 108 minus 5 times the square root of 3 plus 2 square root of 75. Okay, the square root of 3 is simplified. It's the 108 and the 75 we've got to worry about. So the 108, again, the largest perfect square that goes into it is 36. So 36 times 3. The largest perfect square that goes evenly into 75 is 25. So I'm writing 75 is 25 times 3. Okay, the square root of 36 is 6. The square root of 25 is 5. And 5 times 2 will give me 10. So there's my 6 coming from square root of 36. There's my 5 coming from square root of 25. I now do 2 times 5. That gives me 10. I now add up the coefficients. 6 minus 5 plus 10. I get 11 square root of 3. So there's your adding and subtracting. The slight twist is you might have to simplify your radicals first. Multiplying radicals. Okay, multiplying radicals is another place where we usually assume that all variables represent positive real numbers. Again, it's just to make our life easier. Multiplying radicals like multiplying polynomials, or in a word, it's FOIL. Except you have to keep in mind that the square root of x squared is equal to x if x is a positive real number. Remember, if you weren't told that it's not negative, you would need absolute values. So that's a little slight thing you have to worry about. So it's like FOIL with a little extra work. So some examples. Perform the indicated operations and simplify. You may assume that all variables represent positive real numbers. So here's our first one. Square root of 3 plus 5 times square root of 3 minus 7. It's supposed to make you think x plus 5 times x minus 7. So it's FOIL. So when I do my first, square root of 3 times square root of 3, I get square root of 3 squared. Your outer minus 7 square root of 3. Your inner plus 5 square root of 3. And your last minus 35. Okay, notice like the good FOILs, the outer and inner combined, but remember the square root of 3 squared is going to be 3, because you get the square root of 9, which is 3. So combining similar terms and simplifying, the 3 came from square root of 3 squared. In the middle, minus 7 plus 5 gives you minus 2. Notice it'll go even further. You can combine 3 minus 35. The reason we don't do 3 minus 2 is because the 2 is multiplying the square root of 3, and my dear Aunt Sally says I would have to do that first. So I can do 3 minus 35 to get negative 32. So I have negative 32 minus 2 square root of 3. Don't factor out a negative 2 or anything like that. If you're going to factor it, you may as well leave it like this. Number 2, 3 square root of 5 plus 1 times 2 square root of 5 minus 7. Again, it should make you think 3x plus 1 times 2x minus 7. So again, using FOIL. When I do my first, I get 6 times square root of 5 squared. My outer minus 21 square root of 5. Inner plus 2 square root of 5. And the last minus 7. Okay, I can combine the outer and inner to get negative 19 square root of 5. And the square root of 5 squared is 5. So I'll have 6 times 5. Then minus 19 square root of 5 minus 7. Okay, the 6 times 5 is 30. You can combine 30 minus 7. Again, you can't do 30 minus 19 because the 19 is multiplying the 5, and my dear Aunt Sally says multiply first. So 30 minus 7, I get 23. So 23 minus 19 square root of 5. We like to write the number things before the radicals. There is a reason for it. Don't try to factor your answer. Please don't try to factor your answer. You're doing the opposite of factoring. You're multiplying it out. Number 3, 3 square root of x minus 5 times square root of x plus 9. So if we do FOIL, I'll have 3 square root of x squared. When I do my outer, plus 27 square root of x. My inner, minus 5 square root of x. And my last, I get negative 45. Okay, the outer and inner will combine. Okay, and the square root of x squared, remember it's just x, because we're told everything is positive. So I'm going to have 3x. And then 27 minus 5, I get plus 22 square root of x minus 45. Okay, that's all you can do. Do it in this order. Remember, it's first, outer, inner, last. Now, if you think back to FOIL, we could square binomials. We can also square things that look like that as well. So for number 4, I have 3 square root of x plus 5 squared. Now, if you have to do it as 3 squared of x plus 5 times 3 squared of x plus 5, that's fine. But remember, there was a quick way to square a binomial. So remember, square the first term. Don't forget to square the 3. So I'm going to have 9 squared of x squared, which will be 9x. Okay, I want twice the product. The product is 15 squared of x. Double that, I get 30 squared of x. And then square the last. 5 squared is 25. Put it all together, I will get 9x plus 30 squared of x plus 25. Remember, the sign of the middle term is the sign that's in the middle of the problem. Now again, if you have to do 3 squared of x plus 5 times 3 squared of x plus 5, that's fine. You'll get the same thing, and it really doesn't take a whole lot longer. Okay, we're going to go to what's the equivalent of dividing with fractions. So alternatively, you could do this. Okay, your choice. Because in the end, after you write down your final answer, we don't know what you did. So rationalizing denominators and numerators. Okay, this is roughly the equivalent of division. So the fact that we're saying denominators and numerators says we've got fractions. So definition: to rationalize a denominator means to write an equivalent fraction that does not have any radicals in its denominator. Now, it's not that the radicals are disappearing, it's that they're somehow moving out of the denominator. To rationalize a numerator means to write an equivalent fraction that does not have any radicals in its numerator. So again, they don't all disappear, they just somehow migrate someplace else. If when you're doing a rationalization of a denominator and numerator, if you can make all the radicals disappear, you've done something wrong. Rationalizing numerators and denominators is another place where we assume that all variables represent positive real numbers. Again, it's, excuse me, it's just to make our it's just to make our life a little bit easier. Excuse me. Okay. So the method for rationalizing a denominator. The same method applies to a numerator. You just switch the words numerator and denominator around. So step 1. Multiply numerator and denominator by the conjugate of the denominator. When we multiply by a conjugate, you get no middle term. We said we'd take advantage of that later on when we first saw it. This is the later on. Step 2. Simplify. This usually means doing some sort of FOIL and simplifying the radical as well. For rationalizing numerator, we would multiply numerator and denominator by the conjugate of the numerator. Now, from an algebraic point of view, we usually rationalize denominators. In math in general, it depends upon what exactly are you trying to accomplish. Should you go to calculus, you'll actually see situations where you rationalize the numerator instead of the denominator. So let's try some examples. Rationalize each denominator and simplify. You may assume that all variables represent positive real numbers. Here's our first one. 3 over the square root of 3 minus 2. Okay, I want to somehow make this radical disappear from the denominator. So we multiply numerator and denominator by the conjugate of the denominator. Remember, the conjugate just simply changes the sign that's in the middle. So multiplying the top and the bottom by the square root of 3 plus 2. Okay, now in the numerator, since I'm basically lazy, I'm just going to indicate multiplication. I'm going to have 3 times the square root of 3 plus 2. In the denominator, you're doing FOIL. So again, in the numerator, just indicate. Because if I indicate the multiplication, I have factors, and if I want to simplify, I need factors. So when I did the denominator, okay, the first, outer, inner, last. Okay, notice the outer and inner add up to be 0. 2 square root of 3 minus 2 square root of 3 is 0. The square root of 3 squared is just 3. So my denominator is 3 minus 4. Now again, if you feel like multiplying out the numerator, that's fine. I just don't feel like doing it. Okay, 3 minus 4 is negative 1. Okay, this was the last line from the previous line. Okay, this negative 1, I'm going to put the minus up there. Okay, don't write denominators of negative 1 either. So I got negative 3 square root of 3 plus 2, or if you distributed, minus 3 square root of 3 minus 6. Your choice. Now notice, the radical didn't disappear. I just said I no longer have a radical in the denominator. Our next one, 3 over the square root of 5. Okay, secretly the square root of 5 is the square root of 5 plus 0. So its conjugate would be the square root of 5 minus 0. It is its own conjugate. So the conjugate of the denominator is itself. So multiply the top and the bottom by the square root of 5. In the numerator, I get 3 square root of 5. In the denominator, I would get the square root of 5 squared, or the square root of 25. And the square root of 5 squared is just 5. Okay? So again, the radical didn't disappear. It's just that it's moved out of the denominator. And quite frankly, this doesn't look any better than this to me. Number 3, 12 over the cube root of 9. Okay, when you're doing cube roots, or really any root other than a square root, we don't do conjugates. I want to somehow manufacture a perfect cube in the denominator. So we don't use conjugates. So I want to make the cube root of 9 to be, first, it's the same thing as the cube root of 3 squared. I would like to have the cube root of 3 cubed. So I need one more cube root of 3. So I'm going to multiply the top and the bottom by the cube root of 3. If this had been the cube root of 3, I would multiply the top and the bottom by the cube root of 3 squared. Whatever will give me 3 cubed. So multiply the numerator and denominator by the cube root of 3. So the numerator becomes 12 cube root of 3. The denominator becomes the cube root of 27, which remember 27 is 3 cubed. So the cube root of 27 is 3. I can simplify. 12 over 3 gives me 4. So I have 4 cube root of 3. Okay, let's try another one. 5 over the cube root of 2. Okay, I want to manufacture a perfect cube down here. I would like to have the cube root of 2 cubed. Okay, that's what I would like. I would like to have the cube root of 2 cubed. So I need to multiply the top and the bottom by the cube root of 2 squared. Okay, because 2 times 2 squared will give me 2 cubed. So remember the cube root of 2 squared is going to be the cube root of 4. So I have 5 cube root of 4 upstairs, cube root of 8 in the denominator, and the cube root of 8 is 2. Nothing else happens. Okay, the 4 and the 2 can't cancel because the 4 is under the cube root. Number 5. I have 3 over the square root of x plus h minus the square root of x. So we're back to the conjugates. Okay, the conjugate changes the sign between the two terms. That'll become a plus. So I'm going to multiply the top and the bottom by the square root of x plus h plus the square root of x. Okay, in the numerator, I'm going to have 3 times the square root of x plus h plus x. The denominator, I'm going to do FOIL. So I'll have x plus h plus square root of x times square root of x plus h minus square root of x times square root of x plus h minus square root of x squared. Okay, so first, outer, inner, last, when I multiply the denominators. Okay, the numerator, so I'm just going to leave it like that. This, excuse me, this becomes x plus h. This becomes minus x. The outer and inner added up to be 0. X minus x will go away. So that's our final answer. Now again, if you want to distribute the 3, it's up to you. I'm just not inclined to do it. Number 6. I have 3x over 2 square root of x plus 3 square root of y. Multiply the top and the bottom by the conjugate. So the conjugate is going to make that a minus. So I'm going to multiply the top and the bottom by 2 square root of x minus 3 square root of y. Okay, now again, in the numerator, I'm just going to have 3x times that thing. And the denominator, I'm going to do FOIL. So I'll have 4 square root of x squared minus 6 square root of xy plus 6 square root of xy minus 9 square root of y squared. Outer and inner add up to be 0. So I just have 4x minus 9y in the denominator. And again, I'm not inclined to distribute the 3x. You can if you want to, but there's really nothing to be gained by doing it. Let's go ahead and try to rationalize some numerators. So rationalize each numerator. Again, assume that all variables are positive real numbers. Okay, here's my first one, square root of x minus 3 all over 7. So we're going to multiply the top and the bottom by the conjugate of the numerator. So multiply the top and the bottom by the square root of x plus 3. Okay, now in the denominator, this time I'll just indicate the multiplication. 7 times square root of x plus 3. In the numerator, I'm going to do FOIL. So I'll have square root of x squared plus 3 square root of x minus 3 square root of x minus 9. Outer and inner add up to be 0. The square root of x squared is x. So my numerator becomes x minus 9. If you want to distribute the 7 in the denominator, your choice. I prefer not to do it. Okay, let's take a look at one more. Square root of a plus h minus square root of a all over h. So we're going to multiply the top and the bottom by the conjugate of the numerator. So the conjugate will be the square root of a plus h plus the square root of a. So my denominator, I'm just going to have h times that thing. In the numerator, do FOIL. So I'll have square root of a plus h squared plus square root of a times square root of h minus square root of a times square root of h and then minus square root of a squared. The outer and inner add up to be 0. Square root of a plus h squared is a plus h. Square root of a squared is a. I'm going to leave that. I'm not going to distribute the h. I just don't want to do it. So my numerator becomes a plus h minus a. A minus a is 0. So I'm left with just h. And now notice, I can cancel the h's. If I distribute the h, I might not see that. So the h's cancel, leaving me 1 over square root of a plus h plus square root of a. And there's your final answer. You can now see why it's better not to distribute. You need factors in order to cancel. Okay, let's take a look at the last topic of this section. Rational exponents. We will now define what it means to have a rational number, a fraction, as an exponent. Okay, it's going to be a definition. We want to define it in such a way that all of our previous rules about exponents still apply. Basically, it's the 3 laws of exponents, that when you multiply, add exponents, when you divide, subtract exponents, and when you multiply, when you have a power to a power, you multiply the exponents. So we consider a to the 1 over n, where n is a natural number, and a is greater than or equal to 0. This restriction that a not be negative will eventually be dropped. What would happen if we took a to the 1 over n to the nth power? Okay, so remember, a power to a power, you multiply the exponents. So a to the 1 over n to the nth power, 1 over n times n, so third law of exponents, but 1 over n times n is 1, so I have a to the first, which is a. I took something to the nth power and got a. Something to the nth power became a. Remember, in this section, we called that the nth root. So but recall, if a is greater than or equal to 0, then the nth root of a to the n was a. There's the connection. So it looks like a to the 1 over n should be defined as the nth root of a. But now it's too much to expect that all our fractions are 1 over n. So this leads to definition of rational exponents. Definition. Let n be a natural number. Now let a be a real number. Then a to the 1 over n is equal to the nth root of a, provided the nth root of a exists. That's how we take care of it being any real number. The nth root of a has to exist. And in general, we have this. Let m and n be natural numbers, and let a be a real number. Then a to the m over n is the nth root of a to the m, which is the same thing as nth root of a to the m, provided the nth root of a exists. So notice, the denominator is the index of the radical. The numerator is the exponent that goes under the radical or outside. So a rational exponent represents a root. Okay, that's what this definition is telling us, that a rational number as a fraction is a root. The denominator of the exponent is the index of the radical. The numerator of the exponent is the exponent on the base. The usual thing that goes wrong is you get those switched. So some examples. When we write an equivalent exponential expression for each radical expression, do not use mixed numbers and decimals in your answers. So here's our first one. The 7th root of x plus 2 to the 6th. Okay, the base is x plus 2. Okay, when I go to the fractional exponent, remember, the index is the denominator, the exponent is the numerator. So this will be x plus 2 to the 6th seventh. Just leave it like that. Number 2, the square root of x to the 7th. Okay, remember, the index you don't see is 2. That's our denominator. The 7 is the numerator for the rational exponent. So this is x to the 7 halves. Again, just leave 7 halves. Now, in case you're wondering, should you reduce the fractional exponent fraction? Yes. Remember, always reduce your fractions, even if your fraction is an exponent. Now, again, with the definition that we made for the fractional exponents, all the rules about exponents apply. Number 3, the 6th root of y. Okay, the exponent you don't see is 1. So the 1 is the numerator of the fractional exponent, 6 is the denominator of the fractional exponent. So this is y to the 1/6. Number 4, 5 times the 4th root of x. Okay, notice the 5 is not part of the radical, so it's only going to be the x that has the fractional exponent. So this is going to be 5x to the 1/4. No parentheses. Number 5, the cube root of 5x squared. Hey, notice this time the 5 is under the radical. Now remember, if you gave this to the calculator would open a parenthesis there. So if you're going to do it by hand, put 5x squared in parentheses, and then it's to the 1/3 power. let's go the other way. Let's write an equivalent radical expression for each exponential expression. So I've got 4x to the 2/3. Notice I've got the 4x in parentheses. I will put that entire expression under the radical, and I will keep it in parentheses. The denominator is 3, so the index is 3. The exponent is going to be the numerator, which will be 2. So I'll have the cube root of 4x squared. Now, if you're feeling really ambitious, 4 squared is 16. So either one is acceptable. So if the problem has parentheses around something, you just keep the parentheses. Number 2, 7x to the 1/4. Hey, notice there is no parentheses. Only the x has the fractional exponent. Only the x is going under the radical. The 7 is in front of the radical. So the denominator is a 4, so it's going to be 7 times the 4th root of x. Okay, let's approximate each of the following correct to the nearest 100,000ths. Okay, I got 533 to the 2/7. Okay, so set your float to 5, 100,000ths. So your keystrokes are 533, the caret key to take it to a power, and because the exponent has an operation, you need to enclose it in parentheses. So open parenthesis, and then the 2 divided by 7, close parenthesis. Okay, anytime the exponent has an operation, you need to enclose parentheses around it, unless you have one of those calculators that does the nice print that you can tell you're in the exponent. So that, then press enter, and you get 6.01264. Again, if I did my calculator here, okay, turn it back on, okay, clear all this stuff out. So I got 533 raised to open 2 divided by 7. Close, enter. There. Just so you'll know, suppose you didn't enclose parentheses with your exponent. Something radically different. What your calculator did here was it took it 533 to the 7th to the 2nd power and divided that result by 7, which is not what you wanted. Number 2, I got negative 908 to the 2/7. So again, if we do the same thing, okay, open it up, clear, open parentheses, because that's what I have there. Negative 908, close, raised to, open for the fractional exponent, 2 divided by 7, close, 7.00112. Okay, a quick way to use fractional exponents to approximate roots on a calculator. Now again, if you like using that x root key, that's fine. So to approximate the nth root of x on a calculator without using the math key, you follow these steps. Step 1, enter x. Whatever it is, just enter it. Press the caret key. That's your power key. Enter n, whatever it is. Press your x to the -1 key. Press enter. Okay, now whether or not this is any faster than using the math key, I don't know. Pick a method you like and just stick with it. So, approximate the following correct to the nearest 100,000ths. So that's still 5 places. So I've got the 5th root of 158. So your keystrokes would be 158, the caret key, the 5, x to the -1, enter, and you get that. Okay, so again, if I did it here, clear this stuff out. Okay, 158 raised to 5, x inverse, enter. There. Okay, let's try another one. Okay, the 11th root of 574. So you do 574, 11, x inverse, enter. So again, if we do that, 574 raised to 11, x inverse. Okay. By the way, that's what x to the -1 is called. It's called x inverse. Okay. Remember the inverse property? And again, you do need the 0, otherwise you don't have 100,000ths. Now again, the method that you want to pick to approximate your roots is entirely up to you. We don't know what you did. Okay, the end of the material, first section, are